Okay, so the next talk, while the speaker sets up, is going to be on the synthesis of locally symmetric protocols from abstract temporal specifications. It's going to be given by Ruoxi Zhang.
Hi. Oh, great. Hi, my name is Ruoxi, and I'm here to present the paper, Synthesis of Parametric Locally Symmetric Protocols from Abstract Temporal Specifications. This is a joint work with Richard and Kedar. So first, we will start with an overview of the problem and our approach. So this work falls into the category of temporal synthesis, which is a problem of automatically constructing systems from their correctness specifications. More specifically, the realization problem finds processes that jointly satisfy the system-level specification phi against all possible inputs. The realization problem for distributed system is generally undecidable, and the cost to construct distributed systems by computing the product machine is exponential in the length of the global specification. So our goal is to synthesize parametric protocols from temporal specifications. Examples of parametric protocols include network communication protocols, distributed algorithms, and multi-core hardware models. So the protocols we focus on are locally symmetric and composed of k isomorphic copies of a representative process Pn. So here, one parameter we have is big K, which is the size of the network, the number of processes that we have. So we use Pn to denote the representative process, which is a generic process, and Pn interacts with its neighbors. Here is our second parameter, lower k, which is the number of neighbors of Pn. We will use the Denning philosopher protocol on hypercubes as our running example. So in this paper, we introduce a semi-automated approach. So in the first step, given a global specification phi, we reduce it to a local specification phi n that describes the behavior of the representative process Pn. So the local specification is independent of the size of the network, but is still parameterized by the number of neighbors. So then we rewrite the local specification by a counting abstraction to remove its dependence on lower k. Both step 1 and 2 are done by hand and can be automated to some extent, which is considered future work. And then we automatically synthesize an abstract model from the abstract local specification, such that any abstract representative process extracted from the model should be able to be instantiated to form system instances that satisfy the global specification for arbitrarily large big K and small k. So we will use the Denning philosopher protocol to illustrate our approach. So first, globally at the system level, the global specification describes the behavior of all component processes. So in this particular example, big K increases with small k, and the big K is 2 to the power of small k. In each system instance, here we list 3 of them here. In each system instance, both Ks are fixed. And then when we reduce the specification from global to local, we describe the concrete behavior of the representative process. When the number of neighbors, which is small k, changes, the concrete behavior is different. Lastly, when we using counting abstraction to abstract the representative process, we will have a single abstract representative process. And that can take on any configuration of small k and be instantiated for any big K. Then we have some formal definition to describe the computational model. We are interested in protocols that formed by replicas of the same parametric tiling pattern. So the tiling pattern specifies the internal variables of the representative n and the shared variables shared with each neighbor m of n. So in the particular running example, n has 3 internal variables, thinking, hungry, and eating, and n shares with each neighbor m 3 external variables, fork nm, token nm, and dirty nm. When we try, given an underlying network, when we try to construct the system instance, we replicate the tiling process and instantiate it at the nodes of the underlying network. So let's use the particular blue edge, for example. In the Denning philosopher protocol, fnm has the negation value of fmn because they refer to the same fork, and the fork is owned by one of the adjacent processes. And the same goes for the token, but for the dirty and clean status, dnm is equivalent to dmn because they refer to the same fork. So here we formally define the representative process as a set of states, a set of initial state, the transition function, and the transition relation, and a labeling function. Here, a local state of n is labeled by the internal and shared variables. And then for each neighbor m, a joint state is a pair of local state, Sn from Pn and Tm from Pm. The 2 local states must have the same value for all shared variables between n and m. And here is an example joint state. So in the joint state, Pn is hungry, Pm is thinking, and the fork is owned by Pm, the token is owned by Pn, and the fork is dirty. The state transition system of n is denoted by Hn star, and it has 2 types of transitions. One is from a local state of n to another local state of n by the process n itself. For example, the transition from thinking to hungry falls into this category. And then interference transitions from a joint state to another by a neighbor m. For example, if Pm is hungry and sends the token to Pn to request an unowned fork, this transition interferes with the local state space of Pn by changing the variable Tn from negative to positive. And we use dashed lines for all the interference transitions. Then we start to introduce our the main approach of our paper is the specification rewriting transformation. Given the parametric local property phi n that describes the behavior of Pn in the unbounded neighborhood, we are trying to abstract the specification into something that's not dependent on the number of neighbors of n. We use FAIR-CTL as the specification language, and FAIR-CTL makes sure that the path quantifiers for all and exist are performed only on unconditionally fair paths. And since we are only focused on the behavior of n, we use indexed next time properties instead of the traditional next time properties. And we allow FAIR-CTL properties to be parameterized over n. Parameterized over k. So the first example shows that if we have a property says for every m along all the passes globally, the precondition is true, which says the process Pn is hungry without the fork, but with the token. Then along all the next time transitions by n, the post condition is true, which says Pn sends the token to Pm to request the fork. We also allow the VRCTL property itself not be parameterized over the neighbor, but contains terms that are parameterized by the neighbors. So for example, when Pn is in eating with all the forks, and all the forks are clean, Pn in all the next times by n, Pn send the Pn dirty all the forks. One limitation of our method is that the eventualities parameterized over the neighbors are not allowed. So the overall goal of the specification rewriting transformation is to rewrite the parametric local property Vn into an abstract local property Vna, and such that the abstract property should be independent of the number of neighbors. We use an accounting abstraction to do that. We start with two variables to estimate the number of neighbors with a particular shared value, one for accidental and one for universal. And then we write the parametric property into abstract property using the abstract domain. Also, we want to making sure that the abstract local property preserves the realizability. That means if we have some satisfiable abstract model, then it is guaranteed that it can be concretized into concrete models that satisfy the concrete local property. So here is one example. This is our running example from the Denning philosopher protocol. It's about requesting the unowned fork from the neighbor. And given an abstract precondition that says Pn is hungry, has some forks, has some but not all forks, has some but not all tokens, we want to write an abstract property with this abstract precondition. We identify that there are multiple ways to satisfy the abstract precondition. Here we list two of them. The first one says for some neighbors, Pn has the token but not the fork, and for the rest of the neighbors, Pn has the fork but not the token. And in the second case, for some neighbors, Pn has the fork and the token, and for the rest of the neighbors, Pn does not have the fork and does not have the token. So in each of the way, we compute the abstract post condition by applying the parametric update in the parametric property. And in the first way, we know the abstract precondition changes into beta Na, which is Pn since all the tokens. And in the second way, alpha Na remains unchanged. Since we have two post conditions, we put these two abstract post conditions into an abstract property. Here, there exists one transition by n that remains unchanged, and exists a transition by n that changes to beta Na. And the other two transitions are true for all the n transitions. So we describe the detailed procedure for specification rewriting in the paper. Here we just give a brief summary. Given any parametric property with a precondition alpha nm, a universal post condition beta nm, and a set of parametric existential post conditions, we calculate the set of abstract preconditions that is the overall approximation of the parametric precondition. And for each of the abstract precondition, we write an abstract property by doing a case split. So in the first case, the abstract precondition is exact, And in the second case, the abstract precondition is an over-approximation of the parametric precondition. In both cases, the abstract postconditions are calculated by applying the update in the parametric property. But in the second case, just as shown in our running example, when we have different ways to satisfy the abstract precondition, for each of the way, we compute the abstract postconditions separately. Because the indices of the processes are omitted in the counting abstraction, so we introduce context as auxiliary information to represent the concrete changes in the abstract transitions. So the context defines a subset of the over-approximated state set, and the parametric update in the parametric property only applies to this subset. And we use context to concretize the abstract model we have. So on the top right is the abstract structure created from the abstract property, and given a concrete state that shows Pn has two neighbors. The first neighbor 1 has the fork shared between n and 1, and the Pn has the token shared between n and 1. Then this neighbor satisfies the parametric precondition in the context, so it applies the parametric update and get into the concrete post condition. And the concrete structure is guaranteed to satisfy the concrete property with lower k equals to 2. So the overall soundness theorem states that if an abstract model is synthesized from the abstract local specification, then for any number of neighbors, a concrete system derived from the abstract system by concretization satisfies the concrete specification. Then we can instantiate the abstract process with different number of neighbors and different number of processes in the network to form any system instance that satisfies the global specification. And the cost for instantiation is linear in the size of the network. So we avoid the exponential blow-up in the size of the network and the size of the neighborhood. So now the only missing piece is the tableau construction. So like how we automatically synthesize an abstract model from the abstract local specification. We modified the existing iterative tableau-based decision procedure for CTL. So in our modified decision procedure, we first construct the initial tableau from the abstract input specification, and then we construct the next time tableau from the current tableau by traverse the current tableau for transitions that make changes to the shared variable and compute the isomorphic changes and apply interference transitions by the neighbors to the current tableau of n. And we repeat step number 2 until the tableau reaches a fixed point. That means there is no more nodes and edges to be added to the tableau. At that point, we have a fixed point tableau, and we apply deletion rules to remove inconsistencies from the fixed point tableau. If the root is not deleted, then we can extract a model from it. The representative process is just the model removing all the interference transitions by the neighbor. So the key of the construction is to add interference transitions based on existing isomorphic transitions by n itself. So in our running example, we have Pn request send the token to PM to request an unowned fork. So we take the isomorphic transition. That means a neighbor PM, when PM is in Hungary and Pn has the fork, PN has the fork and PM has the token. PM can send the token to request the fork. So that means in the state space of Pn, if Pn has some but not has at least one fork, but not all the tokens, then eventually the interference transition happens because PM sends the token to request the fork. And also the context is isomorphic to the context of the transition by n. In the paper, we proved that the constructed system HNA, which is abstract local model, satisfies the abstract local specification VNA, and the model is closed under neighboring interference and unravels into an abstract representative process PNA. And the worst case cost of synthesizing the abstract representative process is exponential in the length of the abstract local specification, so independent of both cases. So for applications, besides the Dunning philosopher protocols on hypercubes, we also included another application for atomic snapshot protocol on fully connected networks. And the atomic snapshots algorithm implements the snapshot operation that returns the simultaneous state of all the processes. And here is the model, the local model for the atomic snapshot algorithm. If we remove all the dashed transitions, then we have the local, single representative process PNA. In conclusion, our paper reduced the global synthesis problem to the problem of synthesizing a local abstract representative process. So we first write a local abstract specification VNA by hand, and then we synthesize from this specification an abstract representative process. And the abstract representative process can be deployed at the node of underlying networks to form instances of arbitrary size and configurations. So for future work, we plan to extend our work to synthesize protocols for which counting abstraction may not be sufficient. So we plan to extend our work by using a more general abstract domains, and also our approach focus on a single representative process. And we want to extend our work to be able to work with systems with multiple equivalent classes, so multiple Italian patterns and multiple representative processes. So for example, the red-black protocols, consumer producer protocols, for example. And also, we want to apply our work to work with fault-tolerant systems. So that concludes my presentation. Thank you.
So, questions?
Sorry.
Okay, so maybe I have a question. So you are using counting abstractions, and if I remember right, that's just counting the number of neighbors of a process that satisfies a certain predicate, right? That's how you're using it.
Yeah.
So what more would you need? I mean, why is that not enough, or what are the limitations of using a counting abstraction?
I think, for example, we are focusing on Boolean variables. So maybe if we want to handle protocols that has integer values, then we need other abstraction instead of only counting abstraction. Yeah, there are like many other protocols that requires other kinds of abstraction. Yeah.
Any other